Good day, everyone, and those joining us on YouTube. I'm excited to present our research titled Learning to Compose, Improving Object-Centric Learning by Injecting Compositionality. This work by Wei Young, Jaehoon Yu, Sungjin An, and Sunghoon Hong tackles the challenge of aligning object-centric learning with the auto-encoding objective. We've developed a novel method that not only enhances the robustness of object-centric learning, but also significantly improves upon existing approaches. Stay tuned to discover how we've reshaped the landscape of object-centric learning. In this slide, we delve into the key highlights of our research. Our primary motivation is to address the misalignment between object-centric learning and the auto-encoding objective. We aim to enhance the robustness to architectural biases and hyperparameters, which are often sensitive issues in auto-encoding-centric approaches. We also identify a significant problem in the field. Existing methods often struggle with object segmentation, especially when there's a strong correlation between objects and the background. This leads to baseline methods splitting objects into multiple parts and distributing them across multiple slots, which is far from ideal. Our research addresses these issues, and we'll be discussing our approach in the following slides. Stay tuned as we delve deeper into our innovative method and its implications for object-centric learning. Moving on to the key highlights of our approach, we've developed a method that builds upon the auto-encoding framework, but with a significant twist. We've added an additional branch to directly assess the compositionality of the representation. This means we're not just encoding and decoding images, but we're also evaluating how well the representation can be composed from different parts. To achieve this, we construct composite representations from two separate images. This is a novel approach that allows us to capture the essence of both images in a single representation. We then optimize the encoder in tandem with the auto-encoding path. This joint optimization ensures that our method is not only effective but also efficient. In essence, our approach is about creating a more robust and versatile representation of images, one that can handle the complexity of real-world scenes. It's about pushing the boundaries of what's possible with auto-encoding frameworks and opening up new possibilities for object-centric learning. In this slide, we're going to highlight the key contributions of our work. Firstly, we've introduced a novel objective that directly optimizes the compositionality of representations. This means we're focusing on how different parts or objects in an image can be combined to create a new composite image. Secondly, we've extended the conventional auto-encoding approach with an additional regularization on compositionality. This is a significant step forward because it addresses the limitations of traditional auto-encoding methods, which often struggle with object-level disentanglement. In essence, our method not only reconstructs the original image, but also ensures that the composite image is as likely as possible. This dual approach significantly improves the quality of object-centric representations and robustness in training. These contributions mark a significant advancement in the field of object-centric learning, providing a more robust and effective method for image representation and composition. In this slide, we're going to highlight the key aspects of our method. First, we extract object representations independently from two distinct images. We then simulate their composition by a random mixture. This composite representation is then rendered to an image by the decoder. The likelihood of this image is evaluated by the generative prior, which assesses the quality of the composite image. Finally, our encoder is jointly optimized to minimize the reconstruction error of individual images while maximizing the likelihood of the composite image. This approach allows us to improve object-centric learning by aligning it more directly with learning compositional slot representation. It's a simple yet effective method that enhances the robustness to the choice of architectural biases and hyperparameters, which are typically sensitive in auto-encoding-centric approaches. Begin a frame title at key highlights, begin itemize, item key results, begin itemize, item. Our method has shown a significant improvement in FG-RE scores over the baselines in all datasets, with the exception of PTR. This indicates our ability to capture an object holistically. Item, we've also seen improvements in MIOU and MBO scores across all datasets, particularly when the background is monolithic. This suggests our method's robustness in identifying objects even when there's a strong correlation between them and the background. Unlike the baselines, our method consistently captures objects with tight boundaries, demonstrating its effectiveness in learning object-centric representation. End itemize, end frame. Moving on to the key highlights of our work. Firstly, our proposed method consistently outperforms baselines by a significant margin. This is a testament to the effectiveness of our approach in learning object-centric representation. Secondly, we found that regularization on the compositionality of representations is a crucial factor in our success. This technique allows us to capture the essence of objects in a more nuanced way. Lastly, our method greatly enhances robustness to the choice of architectural biases and hyperparameters. This means that our approach is less sensitive to these factors, making it more reliable and versatile in different scenarios. These highlights underscore the potential of our method in advancing the field of object-centric learning. Begin a frame title. Our methodology. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. SRC task underscore execution extracted underscore paper underscore data 2405.00646v1 figures 2405.00646v1 figure 2:1.png. Caption Tiny. The two paths of our framework. Auto-encoding and composition. End a figure. Begin itemize. Our framework consists of two paths. Auto-encoding and composition. In the auto-encoding path, we train an encoder and two different decoders to minimize the auto-encoding objective. The composition path involves extracting composite representations from two separate images and optimizing the encoder to maximize the likelihood of the composite image. We also incorporate a regularization term to enhance object-centric representations, ensuring consistency between the source and composite images. The overall objective is controlled by hyperparameters, which we have empirically found to work well at specific values. End itemize, end frame. Let's delve into the heart of our problem. Our world is inherently compositional. Made up of countless combinations of distinct units, this is a concept that human intelligence has mastered, recognizing our environment as a collection of these composable units. This ability is what allows us to adapt quickly to new and unseen situations. Now, if you look at the figure on the screen, you'll see an overview of our proposed method. Our framework includes two paths, which we'll discuss in more detail shortly. But first, let's understand why this problem is so important. In the realm of machine learning, we're striving to mimic this human ability to understand and interpret the world. However, we're facing challenges with the current auto-encoding frameworks, which struggle to align with object-centric learning. This misalignment is what we aim to address with our method. Stay tuned as we delve deeper into our approach and its potential to revolutionize object-centric learning. Let's delve into the limitations of existing approaches in object-centric learning. As you can see in the figure, our method includes two paths. But before we get into that, it's important to understand the issues we're addressing. Traditional methods often result in suboptimal decompositions. They might capture position or partial attributes, but they don't necessarily capture distinct objects. This is because maximizing the quality of reconstruction doesn't always require disentanglement at the object level. So, while these methods can recreate the scene, they may not provide a clear, object-centric understanding of it. Our method aims to address these limitations, as we'll see in the next slides. In this slide, we delve into the core of our proposed method. As you can see in the figure, our framework includes two paths. The first is the auto-encoding path, which is a common approach in object-centric learning. However, we've introduced a novel objective that directly optimizes the compositionality of representations. This is where our second path comes in. We construct composite representations from two separate images and optimize the encoder in conjunction with the auto-encoding path. The goal here is to maximize the likelihood of the composite image. This dual-path approach is what sets our method apart and allows for a more robust and effective learning process. Moving on, let's delve into the performance of our proposed method. As you can see in the figure, our framework includes two distinct paths. This unique design allows us to consistently improve object-centric learning over traditional auto-encoding frameworks. But that's not all. Our method also enhances robustness to architectural biases and hyperparameters. This is a significant advantage, as these factors often pose challenges in auto-encoding centric approaches. We've put our method to the test on 4 different datasets, and the results have been impressive. Our method outperformed the baselines in each case, demonstrating its effectiveness and versatility. In summary, our method offers a promising solution to the misalignment between object-centric learning and the auto-encoding objective. It's simple, yet powerful, and we're excited about its potential to advance the field. Begin frame. Frame title our methodology. Begin itemize. Item our approach. A novel framework. Begin itemize. Item, we propose a unique method that addresses the misalignment between object-centric learning and the auto-encoding objective. Item, our framework incorporates an additional branch to directly assess the compositionality of the representation. Item, this involves constructing composite representations from two separate images and optimizing the encoder to maximize the likelihood of the composite image. End itemize. Item, benefits of our approach. Begin itemize. Item, our method enhances the robustness to the choice of architectural biases and hyperparameters. Item, it consistently improves object-centric learning over the auto-encoding frameworks. End itemize. Item, implementation details. Begin itemize. Item, we base our implementation on existing frameworks and employ features from the pre-trained auto-encoder to represent an image. Item, for the slot encoder, we use a CNN based on UNet architecture to produce a high-resolution attention map. Item, we also employ an implicit slot attention to stabilize the iterative refinement process in slot attention. End itemize. End itemize. End frame. Begin frame. Frame title, implementation details and learning objective. Begin itemize. Item, our implementation is based on the work of Zhang et al. 2023 with a CNN-based UNet image encoder in the slot attention encoder. Item, we downsample the original 128 times 128 image to a 64 times 64 image using a single layer CNN. Item, the diffusion decoder follows the design of the LSD decoder, with a structure based on the UNet architecture. Item, the surrogate decoder is implemented with the transformer architecture, taking slots as input through cross-attention layers. Item, our framework consists of two paths, auto-encoding path and composition path, with encoder E theta and two different decoders D phi, D psi trained to minimize auto-encoding objective. Item, in the composition path, we extract SC, generate XC with the deterministic decoder D psi, and update the encoder to maximize the equation 6 while fixing decoders D phi and D psi. Item, we incorporate an additional regularization term on the slot attention mask to enhance object-centric representations. Item, the overall objective is controlled by hyperparameters lambda prior, lambda diff, lambda recon, lambda reg, with lambda prior equals lambda diff equals lambda recon equals 1.0, lambda reg equals 0.25 found to work well in our experiments. End itemize. End frame. Begin frame. Frame title, implementation and evaluation. Begin itemize. Item, implementation based on existing frameworks with features from pre-trained auto-encoder for image representation. Item, use of CNN based on UNet architecture for slot encoder and implicit slot attention for iterative refinement process. Item, validation on 4 datasets: CLEVR TeX, MultiShapeNet, PTR, and Super CLEVR. Item, comparison against 2 strong baselines, Slate and LSD. Item, evaluation metrics include FGRE, MIOU, and MBO to measure overlap between slot attention masks and ground truth object masks. End itemize. End frame. Begin frame. Frame title, our methodology and results. Begin itemize. Item, our approach. We've developed a novel method that uses features from a pre-trained auto-encoder and a CNN based on UNet architecture. We've also incorporated an implicit slot attention and a unique slot mixing strategy. Item, datasets. We've tested our method on 4 diverse datasets, including CLEVR TeX, MultiShapeNet, PTR, and Super CLEVR. Item, comparison with baselines. Our method has shown significant improvements over the baselines, Slate and LSD, in terms of FGRE, MIOU, and MBO scores. This indicates our method's superior ability to capture objects holistically and separate them from the background. Item, qualitative results. Our method consistently captures objects with tight boundaries, outperforming Slate and LSD, which often split objects or fail to capture them entirely. End itemize. End frame. Begin frame. Frame title. Technical details of the proposed method. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. A src task underscore execution extracted underscore paper underscore data 2405.00646v1 figures 2405.00646v1 figure 1:1.png caption. A tiny detailed view of the two-path framework. End a figure. Begin itemize. Item the framework's two paths. Begin itemize. Item the auto-encoding path involves training an encoder and two decoders to minimize the auto-encoding objective. Item the composition path extracts a composite representation from two separate images and optimizes the encoder to maximize the likelihood of the composite image. End itemize. Item regularization term. Begin itemize. Item an additional regularization term enhances object-centric representations by encouraging consistency between the source and composite images. End itemize. Item objective function. Begin itemize. Item the overall objective function combines four terms, each controlled by a hyperparameter. The optimal values for these hyperparameters have been empirically determined. End itemize, end frame. Moving on to the technical details of our research, let's delve into the formulation of the problem we're addressing. Our primary challenge is to enhance object-centric learning by aligning its objective function with learning compositional slot representation. This is crucial as it helps us overcome the limitations of existing approaches that often struggle with object segmentation, especially when there's a strong correlation between objects and the background. As you can see in the figure, our proposed method consists of two paths. This framework is designed to not only improve the learning process, but also to ensure that each slot contains the relevant information of an input image. The slots are then constrained to capture composable components of the scenes, such as objects, by regularizing the encoder through the composition path. This innovative approach allows us to generate composite images by mixing slot representations from two images and maximize their validity. In essence, our method aims to make object-centric learning more robust and efficient, paving the way for more accurate and reliable results in the field. Begin a frame. Frame title. Delving deeper into the method. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. A src task underscore execution extracted underscore paper underscore data 2405.00646v1 figures 2405.00646v1 figure 1:1.png caption. A closer look at the two-path framework of our method. End a figure. Begin itemize. Item unpacking the framework. Begin itemize. Item our method is built on an auto-encoding framework with an additional composition path to assess the compositionality of the representation. Item the composition path constructs a composite representation from two images, and the encoder is optimized to maximize the likelihood of this composite image. Item this approach enhances the robustness to architectural biases and hyperparameters, which are often sensitive in auto-encoding centric approaches. Item we also incorporate a regularization term on the slot attention mask to further enhance object-centric representations. End itemize, end a frame. Begin a frame. Frame title. Our methodology and technical details. Begin a figure. Centering. Include graphics. Width equals 0.8 text width. Height equals 0.45 text height. A src task underscore execution extracted underscore paper underscore data 2405.00646v1 figures 2405.00646v1 figure 1:1.png caption. A our proposed methods framework featuring two distinct paths. End a figure. Begin itemize. Item our framework. Begin itemize. Item our method is built on an auto-encoding framework with an additional branch to assess the compositionality of the representation. Item this involves creating composite representations from two separate images and optimizing the encoder to maximize the likelihood of the composite image. End itemize. Item robustness. Begin itemize. Item our method enhances robustness to architectural biases and hyperparameters, which are typically sensitive in auto-encoding centric approaches. End itemize, end a frame, .. On this slide, we delve deeper into the technical aspects of our proposed method. As you can see in the figure, Our framework consists of two paths. This dual path approach is a key factor in the significant improvements we've achieved. Let's talk about these improvements. Firstly, our method has shown a substantial increase in FGRE scores over the baselines in all datasets, with the exception of PTR. This indicates our method's ability to capture an object as a whole, rather than splitting it into multiple parts. Secondly, we've seen improvements across all datasets in terms of MIOU and MBO. This is especially true when the background is monolithic, a scenario where baselines often struggle. Lastly, our method consistently captures objects with tight boundaries. This is a significant step forward from existing approaches, which often fail to accurately segment objects. In summary, our method's technical improvements have led to more accurate and robust object segmentation. This is a promising step towards more effective object-centric learning. Moving on to our technical results, let's take a look at this figure. It showcases the qualitative results of our improved object segmentation. You can see that our method consistently produces better object masks, demonstrating enhanced disentanglement of objects and background across all datasets. Now, let's delve into the key results from our study. We observed a significant improvement in FGRE scores over baselines in all datasets except PTR. This indicates that our method is more effective in capturing an object as a whole. We also saw an improvement over baselines in terms of MIOU and MBO, especially when dealing with monolithic backgrounds. This suggests that our method is more robust in separating objects from the background. Even when there's a strong correlation between them, our method consistently captures objects with tight boundaries, outperforming baselines across the board. Notably, we saw a significant improvement over LSD, indicating that our approach to regularization on compositionality is effective. Lastly, our method showed enhanced robustness to architectural biases and hyperparameters, which are typically sensitive areas in auto-encoding centric approaches. This makes our method a more reliable choice for object-centric learning. Moving on to our technical results, let's take a look at this figure. It showcases qualitative results of improved object segmentation. Our method consistently produces better object masks, demonstrating enhanced disentanglement of objects and background across all datasets. Now, let's delve into the implications of these results. Firstly, we see a consistent improvement of object-centric learning over auto-encoding frameworks. This is a significant achievement, as it addresses the misalignment between object-centric learning and the auto-encoding objective. Secondly, our method shows robust identification of objects, even when there's a strong correlation between the object and the background. This is crucial for real-world applications where objects often blend with their surroundings. Thirdly, our method has the ability to capture an object holistically into an individual slot. This means that each object is treated as a separate entity, which greatly enhances the quality of object segmentation. Lastly, our method has proven its capability to handle complex real-world datasets. We demonstrated this on the BDD100K dataset, which consists of diverse driving scenes. This shows that our method is not only theoretically sound, but also practically applicable. In summary, our method provides a robust and effective solution for object-centric learning, with promising results on real-world datasets. In conclusion, our paper's primary objective was to address the misalignment between object-centric learning and the auto-encoding objective. We aimed to improve the robustness to architectural biases and hyperparameters, which are often sensitive issues in auto-encoding centric approaches. To achieve this, we introduced a method based on the auto-encoding framework. This method incorporates an additional branch to directly assess the compositionality of the representation. This innovative approach constructs composite representations from two separate images and optimizes the encoder jointly with the auto-encoding path. Our extensive experiments have shown that this framework consistently improves object-centric learning over the auto-encoding frameworks. It also greatly enhances the robustness to the choice of architectural biases and hyperparameters. In essence, we've developed a method that not only addresses the challenges of object-centric learning, but also enhances the robustness of the learning process. This is a significant step forward in the field, and we're excited about the potential applications and future research opportunities it presents. Begin our frame. Frame title of the learning objective and composition. Begin itemize. Item. Our framework consists of two paths, the auto-encoding path and the composition path. Item. In the auto-encoding path, We train the encoder and two different decoders to minimize the auto-encoding objective. Item, the composition path extracts a composite representation and updates the encoder to maximize its validity. Item, we also incorporate a regularization term to enhance object-centric representations, ensuring consistency between source and composite images. Item, the overall objective is controlled by hyperparameters, which we have empirically found to be effective at certain values. End itemize, end frame, begin frame title conclusions and remarks, begin itemize, item key takeaways, begin itemize, item we've introduced a novel method that addresses the misalignment between object-centric learning and the auto-encoding objective. Item, our method, despite its simplicity, has shown consistent improvement over the auto-encoding frameworks in object-centric learning. Item, we've also demonstrated that our method enhances the robustness to the choice of architectural biases and hyperparameters, which are typically sensitive in auto-encoding centric approaches. Item, our framework incorporates an additional branch to directly assess the compositionality of the representation, which has proven effective in our extensive experiments. End itemize, end frame,